This is the MIT Integration B qualifying exam for 2024. Quite hilariously, you were given 20 minutes to do as much of this as you can. I think the tactic should just be to spot the ones that are easy and just try and do those as quickly as you can, and then think about the ones that are harder. But anyway, let's see if I can do this in 20 minutes. The first integral is a joke integral. This is a line 2024 up high, and it goes across 2, so the area is just 2024 times 2. This one is immediately difficult. I think the best way to do this is to raise the entire integral to e to the log of that thing, because of course these two things would cancel, so I'm just doing this. But the reason this is helpful is because of course log of something over something can be written as log of something minus log of the other thing. And now of course, based on log law power laws here, we can bring this log down to the front of the other log, and this log down to the front of the other log. And now we can see that we have the two same things multiplying, which is all going to cancel out. You get e to the 0. E to the 0 is 1, and then you integrate it to make x. Probably more interesting ways of doing this other than just doing parts. That's what I did. So integrate x for x squared over 2, keep that the same. Differentiate this for 1 over x and keep that integrated, and you get this. Take away integral over in the middle, and then of course you can integrate this for just x squared. And now this is just, x over 2 integrates to x squared over 4. And we end up with this. I could tidy that up, but I can't be bothered. Number 4, we just need to factorize out the x on the bottom and then sneakily write it on the top like this. And now this is of the form f of x on the bottom and f dashed of x on the top. So this is going to integrate to log of the bottom. So it's log of x plus 2. This is horrendous, so I'm not going to do it. Lol. Question number 6, we can just factorize out a cos of x from the top row, which will leave behind a 1. And then this is cos over sine, right? So we would just have a 1 over sine left over. This is 1 over sine, so if you pull a cos out of it, you get a 1 over sine cos on the bottom. And then, of course, if you pull out a cos of that, you get this. Very similar when you pull a sine out of the bottom of this one. And then, of course, you notice that these two brackets are identical. They cancel. And the integral of this, again, it's f dashed over f, isn't it? So it just integrates to log of sine. Difference of two squares is going on here. Difference of two squares here to make this, and then do it again to this one to make this. Cancel these two things out, expand the rest of it, and then integrate every term very boringly, and you get this answer here. Number 8 is equally boring. You just expand it all out, and then you put in 1 and, well, you integrate first, of course, and then you put in 1 and minus 1, and then you just have to very, very boringly just do the maths and try not to make a mistake, which I hope I didn't. And you end up with this here. Good. For number 9, sine x plus cos x can be written as root 2 sine of x plus pi over 2. I've done an R formula here just very quickly, but if you expand this out, you get sine of this, cos of this, which is 1 over root 2, which will cancel with that just to make sine. And then sine of this, which is 1 over root 2 cancels, and then cos of this, and then you get this. That's fine. Now, the thing is, the sine graph between 0 and 2 pi integrates to make 0. The fact that there's a root 2 here doesn't matter, because that just makes it taller. It's still the areas are still going to cancel out to make 0. And also the fact that you're shifting it to the left a bit also doesn't matter, because any area that you gain shifting to the left in one space, you'll lose when the other bit comes out from the other bit. And of course, when you raise it to power 11, that just makes it taller. It doesn't do anything. In fact, no, it makes it shorter, right? Because you're always between 0 and 1. But it doesn't do anything to the signs. So this is all just going to be 0, just by the symmetry of sign. Sinh plus cosh is e to the x. So this is e to the 11x, which we can just immediately integrate, and that one's really nice. This one here, if this was a sec squared, this would be super easy because it would just be inverse chain rule. Or no, sorry, is it chain? No, reverse chain rule. That's what it's called, right? So, but it's not a sec, it's a cosec. So what we can do is we can cancel it with a couple of there, and then pull out 2 of the cos from here to make a tan to the 2022 here and a sec squared here. And now it's just a reverse chain rule because we can just say that this is tan to the 2023 over 2023, and then the sec squared would come from deriving the tan, and we're done. Question 12 is quite interesting. Just take this object, cos x to the power x, and just differentiate it. Now, to differentiate something to the power x, you generally need to take log of both sides, because then you can pull the x down to the front. And now we can differentiate this. This just differentiates a bit of, what's it even called? Implicit differentiation, is that what it's called? Is it? Yeah, it is that. So it's 1 over y dy by dx, and then you can differentiate this to get it to go away, leave this alone, and then leave that alone and differentiate this for this. And now what you notice is this is just tan of x. The minus can go there. and you can times both sides by y, but y itself is this, and you end up with precisely the thing that you're trying to integrate. So this thing differentiates to the thing you're trying to integrate, which means this thing integrates to this, and we're done. Quite a nice little question. For this one, you just need to know this result, apparently, which I just copied very badly from Google Images. But of course, we can put this 4 into the square like this. 2 squared is 4. And then we can use the substitution u equals all that stuff. Du is therefore just a half, so we just need to times this whole thing by 2 when we put the u in. And then by this result, that's just root pi, so this is 2 root pi. Okay, next one, make the substitution u equals this thing up here. Feels fairly natural. Notice how this thing is just the derivative of this thing, which is hopefully quite helpful. So okay, bring this thing down, or differentiate this thing to get this. And then, of course, we can divide that and then put this over there as well. This is just u, though, remember. So I think that looks a bit like this when you do that. Put all of that in. But the thing about this that's quite interesting is when you put in, when you're changing these bounds here, when you put in e to this as your x's, you get e to the e plus 1 over e. But when you put in 1 over e, you get e to the 1 over e plus 1 over 1 over e, which is just e. And these two things are the same. And so when you cancel these two things out, you just end up integrating e to the u over u between the two same numbers, which is just going to be 0. So kind of interesting. For 15, nice little trick here. Pull out an e to the x from this object here to make it, so of course to make it here, because of course you would add these powers up and these x's would cancel to get you this. Now put this e to the x into there, and now what you can notice is that this object here is precisely this object up here differentiated, because product rule gets you this bit, and then the minus 1 comes from there. So this just integrates to this whole thing there, and you're done. Lovely little question. Here, arctan differentiates to 1 over 1 plus x squared, and arctanch differentiates to 1 over 1 minus x squared. So this one is sort of differentiating to make this times arctanch, and this is differentiating this over 1 arctanch. So therefore, this is the reverse of a product of just arctan arctanch. Because if you differentiate this one, you'll get 1 over 1 plus x squared times this, which is this term. And then when you differentiate this one and leave this alone, you get this over this. And you're done. For 17 and 18, we need to evaluate some sums. So, okay, let's just put in k is 0, k is 1, k is 2, and so on. You get this. This term is just 0. This is just x to the 1, because that's 1. This is 0, so this goes away. This is minus 1 to make a minus, and then the next one will be 0, and the next one will be 1, and then minus 1 and 1. You'll end up with this series here, which is a infinite series starting at x, and then having a r of minus x squared. So therefore it's just a over 1 minus r, which is a over 1 plus this thing, minus minus. And of course this just integrates to a half log of this thing, because this differentiates to x, so you just need to halve it, and you'll get your answer. Our second sum is a little bit more complicated. We need to firstly just sort of put the numbers and see what happens. So when you put in 0, you just get 2 to the minus 1012. When you put in 1, you get 1 minus that, which is this, and all the way up to this. And now what I just did was integrated every term separately. So let's add 1 to this power and divide by that number. Add 1 to this power, divide by that number, and so on all the way to the top. And the thing is, when you put in 1, the powers don't matter, because 1 to the power anything is 1. And when you put in 0, the powers don't matter, because 0 to the power 0 is 0. So when you put in 0, all these terms go away. And when you put in 1, you just have the coefficients adding together. So we just end up here. Now, what I need to do to this is I'm just going to sort out these terms on the left. And I'm going to write this as 1 over 2 to the 1012. Sorry, yeah, 1 over 2 to the power 1012. And now if I combine this denominator here by writing this as 2 to the 1012 over 2 to the 1012 and putting it together, I get this. And now flick this guy to the top. I'm doing this the same thing for all of the negative ones to the middle. Put those on the top and you get this. And what you can notice now is that if you add this very first term with this very last one, you're just going to get 1, because the numerators add to make the denominator. And the denominator is the same, so I can do that. So this one and this one just make 1. And so do this one and this one. And so do the 1010s and then the 1009s. They all add up to make 1. So we're going to have 1112 lots of 1 going all the way to the middle. The middle term is this, which has no body. So it's just going to be 1 times 1012, 1012 times, plus this term here, which is just a half. And so we're going to get 1012.5. For question 19, we just need to desperately try and make this denominator in the numerator, except we can't because we've only got 1x to the 4, whereas we've got 2 down here. So what I'm going to do is I'm just going to build half of the denominator in the numerator. So I'm going to write out the denominator in a sensible order first, and then I'm just going to halve every term and write it up here. Now the reason I'm going to do that is because this entire thing is now just a half. And now I just need this term over here to kind of cancel out everything I put in. So I've taken away a 2x cubed by magic, so I'm just going to need to add that in. I've added that in, so I'm going to take it away, and so on. Now, this is, like I said, just a half. Look closely at this term, though, because if you differentiate the denominator, you're going to get 8x cubed, which is 4 times this. You're going to get 12x squared, which is 4 times this, 12x, which is 4 times this, and 6, which is 4 times that. So this here derives precisely to its own numerator as long as you divide it by 4. So therefore, this is just a half, as I said, which integrates to a half x, and this thing integrates to a quarter log of the denominator, and we're done here. And question 20 to finish up, we're going to set y equal to this whole thing up here, and except these two terms here, by definition, are just each of the original term. So this here is just y, and this here is just y. And now if you times both sides by 1 plus y, you get this, cancel out the y's, you get this, and square root. And so I think I can literally just replace this whole thing here, because it's equal to y, with this whole thing here. So I'm just going to put it in. And now I can, of course, integrate in normal, and I'm just going to put the numbers in. And I think